You see in the title that I changed a bit my focus. So global datasets are still in focus, but I also brought you a local case study. So actually two case studies, one global one local one, because I thought I wanted to like go across scales and sectors to really cover the whole spectrum and the data we were using and the challenges we were facing. And I'm also addressing collaboration with stakeholders. I would like to start with the global study we have recently finished, also within CNDS. So I finished it with, or was working with Giuliano Di Baldassare mainly. So we were actually inspired by a recent paper by Günter Blöschel, who is now my advisor at the Vienna University of Technology. And he published in Science on changing climate shifts or changes of timing of European floods due to climate change. And so we're not talking about changes in the frequency or magnitude of an event. We're talking simply about the timing. When does a flood occur during the year? And we were wondering, because we were facing these droughts in the northern hemisphere, including Sweden. We have heard about it today. What about droughts, actually? So we wanted to know, have droughts shifted in the timing? And we were specifically interested in dry spells. Dry spell is simply a period of consecutive days without rainfall. So you could say it's a special type of drought, a special definition of a drought. And the problem is that climate research has also in that respect, in terms of droughts and dry spells, mainly focused on the changes in the frequency, but not in the changes in the timing. And the point is that the within year timing of a drought or a dry spell, it can be a severe threat. So if you think of, for example, wildlife, so animal migration, for example, energy production, water security, this is all strongly dependent on when such an event occurs. And we were particularly interested not only in the timing itself, so the hazard part, you could say. We were interested what does it mean for agriculture, for crops. So we wanted to bring together the timing of dry spells and crops, because you sow a crop at some point, you harvest it, and in this growth period of the crop, there are periods where they're particularly prone, the plant is particularly prone to a drought. So the timing plays a big role. And so the goals of the study was actually that we wanted to derive simply the hazard, so the within year timing of extreme dry spells over the last decades. And then we wanted to link it to the crop sowing and harvest dates. And then we wanted to analyze the potential impact. So what does it mean in terms, for example, global food security? What data did we use? Now we talk about global data. We used data from the Global Historical Climatology Network, GHCN. And that's actually a data set with daily summaries of land surface stations across the globe. And it's actually a beautiful data set. We have over 100 stations in 180 countries and territories. So it's a very nice data set. That's the first data set we used, and it's consistent data set, which is very important. And in terms of these crop sowing and harvest data I was talking about, there is a publication in Global Ecology and Biogeography, highly cited paper, I think 400, 500 citations, by Sachs and al. And they provide global sowing and harvest dates in two different ways. One, you have georeferenced point data, and you have global grid data. We wanted to bring together these two data sources. And you can see here, it comprises 6 different data sources, which you find in the table. And there also you see there's some uncertainties, because these data provided a different geographical resolution, for example, and they also had a hard job, of course, to join these data, to merge these data. In terms of the rainfall data, you will see now basically in this map all the stations that we could analyze, because for dry spells analysis you need quite complete data. 90% is what you should at least have. And so we analyzed the trends in terms of the timing, and what you can see here is basically, so all the points are these 3,600 stations of 11,000 that we could analyze, and you can see we could only use the red ones. Those are the ones that are 90% complete. And you can see at the same time that we have a huge issue in low-income countries. Actually, we wanted to do a global analysis, but then we realized, for example, Africa, where we think that food security is probably more important than in Europe, we could not do any analysis. There are no data. They are not complete enough to do the analysis. And this is an issue we're very often faced with global data, that in the regions where we might be most interested in, we don't have any information. Still, for this study, it's very relevant because the 4 regions, we have mainly the US, Europe, China, and Australia were quite complete. These regions contributed about 50% of the or contributed 50% of the major staple crops in 2017. So it's still quite relevant. Very quickly on the results. So this is a result on the hazard component, the shifts on timing between two 30-year period, 56 to 85, and then 86 to 2015. So we want to understand how has it changed between these two 30-year periods. Green means earlier occurrence, and this pink lilac color means later occurrence. You can see it's quite diverse in terms of the results. For example, we have here Europe, where you have an earlier occurrence in large regions than China, which is more later, but it's quite diverse. You don't really see clear patterns. Still, you can see there have been a lot of changes in the last, in this 60-year data set, basically. Quickly on the SACS data, we used the gridded data set. So what they did, basically, they used the georeferenced locations. You have the day of the year. This is an example when wheat, for example, is sowed, a mean date during the year. And then they extrapolated to have a global grid data set. And also here, of course, you see there are a lot of uncertainties. We have very little points, for example, in Asia. Then they extrapolate. So you also have to be aware that there are a lot of uncertainties in these data. And then we put everything together, simply speaking. And these are two examples. What you can see in the top row is from the SACS and ALT dataset, seeding and harvesting date. The x-axis is the day of the year, so 1 to 365. And then for these two 30-year periods, the earlier one and the more recent one, and that's basically from our analysis when the dry spell occurs, the extreme dry spells during the year. And here you can see, for example, that in the more recent data, it's occurring earlier. It goes more into the seeding period, which is an issue because crops are very sensitive after the seeding period, the so-called vegetative growth period. So here we could say, okay, we assume this could have been an issue. And the same, for example, for another example from Romania, where actually the occurrence of the dry spell was most likely outside the growth period, and now in the last 30 years it was within the growth period. But we also saw other examples where it was exactly the other way around, that it seems that risk has been reduced. So to summarize it, around a large number of these stations had statistically significant trend. I talked about these patterns that are spatially variable, and then we concluded that some regions might have benefited or might have suffered from these consequences, or will suffer if the trends that we observed will continue. But we still think we should be aware of these changes and maybe take them into account when we think of adaptive capacities in agriculture. And also the methods that we developed in that context are very universal, so you could use it also to other data sets. For example, if you have nice data for Africa, you could still use the same methodology. But we must be aware with this global data set of these, all these uncertainties. Now we go local. That's a case study from Salzburg. Salzburg, that's where I did my PhD. You see, it's a gorgeous place. It's probably one of the nicest cities I know. I've been so far in my life. I'm very honest about that. The river that you see here is the Salzach River, so it's close to the Alps, and it's a gorgeous place, as I said. But Salzburg, what I'm presenting now is basically from a publication in the Journal of Flood Risk Management, and that we published together with University of Innsbruck back then the Salzburg University and Bristol. And Salzburg can also look like this. This was in 2013. You might recall we had major floods across Europe. And the event on the 2nd of June basically was above the 1 in 100 year flood, the official 1 in 100 year flood. So a quite massive flood event, a so-called pluvial or river flood. But that's only part of the story if you think of floods. Usually people think of exactly that type of event when we talk about floods, but a flood is also this, and we heard about this today in context of this SPLASH project. Pluvial floods, rainfall-triggered floods, not related to a river, heavy downpour, thunderstorm, you see something like this. Also a major issue. So on that day, on the 20th of June, the year before, this major river flood, we had 45.5 millimeter per hour, highly intense rainfall. It was in the period after 1994, or within 1994 and 2012, the highest observed hourly rainfall amount. And I was wondering, how likely is it that these events occur simultaneously? Could that happen, like a mega event? And that was the idea of the study. So a multi-hazard approach for these two different types of floods. And we wanted to use, I don't go too much into detail from the academic approach here. So for here, it's important to understand, so when do we have days, or how likely are they that we have a major river flood here and a major pluvial rainfall triggered flood at the location at the same time. So wanted to understand the frequency of these joint events. Well, if we simulate it, it's quite simply to find out when is a river flood an issue. Well, we have hydraulic engineers, and they can tell us a 1 in 100 year flood. When the riverbank is full, at some point it gets flooded. It's much more tricky when it comes to these pluvial floods. So which intensity actually might trigger a flood? And that was a main issue in this study. Why is it so complex? Well, think of urban environments. You have a complex topography. You have a sewage system that might be functional or blocked. It's also the temporal resolution. In that case, we used our resolution, but a 5 millimeter downpour can also trigger floods. So-called IDF curves. For the engineers here, they might be aware of that. But the literature told us when we did that study that around 30 millimeter per hour is an issue. And also for the UK, the Environment Agency, they have an extreme rainfall alert, and also there is this magic 30 millimeter per hour threshold. We were wondering, can we confirm that in our study? Because that's what we needed, this critical threshold. And for Salzburg, what we did basically, we wanted to use a simplistic approach. You could call it a back-of-the-envelope approach. And we used two additional data sets. One was of a local insurance company, and one was of the local fire department. And the insurance company was an Austrian company. They provided us with anonymized, of course, claims data, including information, the date of the loss, the address, the type of loss, and the monetary damage. And of course, if you know when damage happens and where, then you can link it to your rainfall observations to understand when is the rainfall critical. But we have to be aware there are multiple issues with insurance data. First of all, if there is a rainfall, it doesn't mean if somebody has a damage that he will claim it to the insurance. Sometimes people say, I'm not going to do it because they will kick me out of my contract, or they will increase my premium. Fraud is also possible. We had cases in the past that people knew the flood was coming, then they would put their TV set into the basement. It's an exception, but it happens. And then a portfolio might not be really representative. Maybe you have a really accumulated risk somewhere in one part of the city, and then very often contracts are complex. You have deductibles and limits and all these things, and it's not always clear from the data if they have already applied, and so you have to be very careful in terms of the data that you get. Fire department data, very simple. I talked to them. They were very nice and very collaborative, and I asked them for operation records for every day in a 20-year period, I think, where the rainfall was higher than 15 millimeter per hour. So we got the date of operation and the number of operation, and only, of course, operations when there was flooding. For example, when they pumped out a basement. And this was aggregated for the whole zip code of Salzburg. They offered at some point also to give us address data, but we didn't use it also in that study, and then we didn't need it anymore. But they also offered it. But they were a bit critical also about that. They were not, for the insurer it was fine, but they were much more critical in terms of, data security and stuff. Good. Very simple. So we did this back of the envelope approach to test for this 30 millimeter threshold. And what we did basically is we just clustered them into different classes, 0 to 10 millimeter, 10 to 20, 20 to 30, and larger than 30 millimeter. And in terms of rainfall and the fire operations, we saw more like a linear trend. But if we looked into the rainfall versus the insurance claims, and this is just claims, so it means if somebody has claimed a damage, we didn't look into monetary damage. You can see that as soon as we reached this 30 millimeter, suddenly the claims went up. So to us, this was kind of a confirmation, okay, maybe there is an element of truth in this threshold. Again, really back of the envelope, but it gave us some evidence that it might be useful to go for this threshold. Good, so that was actually were these two local data sets. And then what about these joint events? We simply looked, okay, for different windows. Window 1 means occurring on the same date. Window 7 means within a week. We looked, okay, is there a critical river flow and is there a critical rainfall? And we looked into different thresholds. Even though 30 was kind of confirmed, 30 millimeter per hour, we also looked into 20 and 25, and we found out, for example, that a critical river flow and a critical rainfall occurs at the location at the same time, has a very high return period of around 3,000 years. So I would say highly unlikely. And of course, if you reduce the threshold, it becomes more likely. And if you widen up the window, of course, it also, the return period goes down, so the probability increases. Still, we found out that these joint events have a very low probability. Why is that relevant? Well, for the fire department, for example, they might still be focused on separate events, so they might not be afraid of the fact that they know a river flood is coming or it might happen, then they have to put up their mobile flood defense and all these things, what you see here in the picture, and at the same time there might be a rainfall triggered flood and they have to go to all the basements and pump it out, so they realized, okay, this is probably not an issue, which is a result. And the insurer might not fear this kind of multi-hazard mega event. But this is a purely statistical model that we developed, really purely statistical with some physical components. But we have to be aware there might be, for example, weather situations that might change these in the future, especially when we think of climate change, might change these probabilities completely. So so-called black swan events, we don't understand right now what really happens. We only take the observations and we extrapolate, which is always dangerous. So that's what we should be aware of. And then I have two more sentences, and this is especially for our young PhD researchers. When it comes to collaboration with stakeholders, because this is was my experience with the fire department and with the insurer. So usually you request the data, you offer the collaboration, then you do your research, and you should maybe also provide an update to them every now and then. You disseminate and publish, and very often this cycle is not closed. So I was told that it happens that people come, researchers come, they ask for data, they do their stuff, and they never get back to them. And of course, that is very annoying. So I was really told, also by my supervisor back then, go back to them, feedback into your results, tell them what you have achieved. This is super important. And by that, you can also establish a long-term collaboration. Thanks.